If you recall, yesterday we were talking about double integrals, but in polar coordinates. And we highlighted the thing that we need to do. So today we want to upgrade that to triple integrals in other kinds of coordinates. So if you recall, a double integral over some region R of a function f dA. The dA in rectangular coordinates is a dx dy or a dy dx. This works because dx and dy are both length. They're both changes in length. So this I could write the dx as a length, and the dy can be a width. So the dA is a little rectangle of area that we're evaluating the function f at and using that as a height, so that the area is just length times width times height. In a double integral, we also describe the xy plane in polar coordinates. So polar coordinates we had to do something different. So in polar coordinates, we wrote r d theta dr. The reason we have to have this extra factor of r, the reason that we need this extra factor of r is that d theta is not a length. D theta is not a length. The dr is a length. It's a small change in distance. So we could use dr as a width. But we need the r to make d theta into a length. And so we're using arc length. So the dA needs to be a little square or a little rectangle in the xy plane. So it's dx times dy, small change in x, small change in y. Evaluate the function at some point in that little square. In polar coordinates, we approximate that square with r d theta dr. So we're using arc length. Any questions? Now we want to move on to triple integrals. So we're going to have 3 coordinates. In rectangular coordinates, we just get x, y, and z. So a triple integral in rectangular coordinates where we have a dv, we can write the dv in rectangular coordinates, and that's where we started. So in rectangular coordinates, we have dz, dy, and dx. And this works out. This makes a volume because dz is a length. dy it can be the width. And dx can be a height. Length times width times height, that's what gives us a volume. It's a little box in which we're evaluating the function. It's saying the function is constant throughout this little box, dx, dy, dz. So today we want to introduce new kinds of coordinates. And it works very much like polar coordinates. We take one of the lengths and replace it with an angle. But we get 3 to choose from. So we start off taking one length and replacing with an angle. That gives us cylindrical coordinates. And then we replace 2 lengths with an angle, and then we get spherical coordinates. So we got 2 other kinds of coordinates. We're going to have cylindrical coordinates. And we're going to have spherical coordinates. So first, we need to describe how cylindrical coordinates and spherical coordinates work. Any questions before we get started? Here's how we want to think of cylindrical coordinates. Cylindrical coordinates are just polar coordinates plus a z-axis. We just take, just like with rectangular coordinates, we have the xy plane, and then z goes up from there. Now we just replace the xy plane with the r theta plane, and z goes up from the origin like normal. So cylindrical coordinates are polar coordinates plus a z-axis. Cylindrical coordinates, polar coordinates plus z-axis. So cylindrical coordinates are going to be polar coordinates. That's our floor, and we'll have a z-axis above it. So that's the easiest one to think about. So in cylindrical coordinates, we'll have the z is just going to be the height above a point in the xy plane. But instead of marking this point with x and y, we're going to list this point as r, theta, and z. So that point will be r, theta, and z. The r and theta are the same r and theta that we had in polar coordinates. R is the distance from the origin to the point underneath. So there's r. Theta is the angle measured from the positive x-axis towards the positive y-axis. So this is the same r and theta that we had in polar coordinates. We're just adding z as the height above that point. Think of cylindrical coordinates as the cylinders are the markings that we would have on graph paper, well, three-dimensional graph paper. So on rectangular coordinates, the graph paper looks like a grid. On polar coordinates, there's one pole in the middle, and it looks like all these angles coming out. Cylindrical coordinates just take those circles that we see in polar coordinates and extends them up for the z-axis. In this case, if we write d theta, dr, dz, that's not going to give us a volume because d theta is not a length. So we still have the same issue. So dV, if I write d theta dr dz, d theta is not a length. D theta is a change in angle. So multiplying d theta dr dz does not give me a volume of a little box. I need to turn theta into an arc length, and we do it the same way we do in a double integral and polar coordinates. We just multiply by r to make an arc length. So that r in the dv in cylindrical coordinates turns d theta into a length. Then dr can be our width. And dz can be a height. In rectangular coordinates, dx, dy, and dz, those are all lengths. So dx, dy, dz measures a volume. But in cylindrical coordinates, d theta is not a length. We have to multiply by how far that theta is from the origin to turn d theta into a length. Any questions? So if you're looking at a function in cylindrical coordinates and you're integrating in cylindrical coordinates, your dv is going to be r d theta dr dz. As long as we have that r there, the d theta, the dz, and dr can all go in whatever order we want. The r doesn't have to go with theta. So at that point, we just integrate whatever is most convenient for us at the time. But we need r to turn those three d's into a volume. Any questions? Cylindrical coordinates is polar coordinates plus height. How's everybody okay? Let's take a look at spherical coordinates. In spherical coordinates, we're going to be replacing two coordinates with an angle. So there's only going to be one length. We can't go any further than that. We need to have one length. Like if I give you three angles, you can't solve a triangle because there's no idea about how long any of the sides are. I have to give you at least one side. So one of them has to always be a length. That's why we can have x and y, length and length. We can have r and theta, that's a length and an angle. Rectangular coordinates in 3D, x, y, and z, it's a length, and a length. R, theta, and z is a length, an angle, and a length. Spherical coordinates is going to be a length and two different angles. I just got to tell you where those angles are measured. So let's look at spherical coordinates. We're still describing three-dimensional space. So I'll still draw in spherical coordinates, we're only going to have one length. And that is going to be, I'm going to need this one down here. Okay, now we can see the door swinging between the X and Y axis. For spherical coordinates, we only get one length. So we've only got one choice for what that length should be. That length is going to be the distance from the origin to the point. And that's typically called rho. So rho is the distance from the origin to the point. And I put rho in exactly where I didn't want to put it. I even said myself on my way over here, don't put rho in the space that you need to write more stuff. Now we're going to use two angles, one of which we're familiar with. The angle theta is the same angle theta that we had the angle theta is still the angle from the positive x-axis rotated towards the positive y-axis to a point underneath the point that we're concerned with. So the theta is still the same as in the polar or the cylindrical coordinates. Now we need to build another angle, and we have lots of choices. Here's the one that we went with, like I was there. So the second angle is going to be phi, and it's going to be measured from the positive z-axis down towards the point. So phi is measured from the positive z-axis down to that point. Now our three variables, rho, theta, and phi, one of them is a length, the other two are angles. So if we're going to make dv out of d rho, d theta, and dv, we're going to need to turn d theta and d phi into lengths. And we're going to do the same thing. We're going to use arc length to do it. So I'm going to have to add factors to d theta and d phi so that those will represent lengths so that we can get a volume. We're gonna have to fill in some stuff. So d rho is a length, but d theta and d phi on their own are not length. So I need to add some extra factors to make them into lengths. And we do the same thing. We just use arc length. We just need to know how far from the origin are we? D phi is actually the easiest one. Notice that rho is one of the sides. So if we have an angle, a change in the angle phi, rho is right on there. So we can just put that in for our arc length. One of the side, rho is sitting on one of the sides of the angle phi. So I can just use rho as the distance from the origin to the little box dv to turn d rho into a length. Note that rho is not one of the sides of the angle theta. But if we drop rho down, if we project rho down into, down onto the xy plane, that will be the distance. So I need to look at this from the side. If we look at this from the side, here's our z-axis. Here's our xy plane. Here, I'm going to look at the plane containing this door. Here's rho going up to the point. Here's the angle phi. So I'm just going to drop down so that I'm looking at this from the side, and so that I can't see any difference in the xy plane. I can't see what's going on with the theta. But what I need to know is how far is this point on the floor from the origin? I need to know how far that point is from the origin. That's what's going to go in as the factor that turns theta into a length. That is the side that length is one of the sides of the angle theta. So I need to know how far that point on the floor is from the origin. Notice that that's the same distance as this angle up here, or this side up here. And so I could use this right triangle with a hypotenuse of rho. And the distance that we're looking for is opposite the angle phi. So that tells me that I want to use sine. The sine of phi is the side that we're looking for times, I said sine of phi. Sine of phi is the side that we're looking for, the opposite over the hypotenuse rho. And so the opposite side is rho times the sine of phi. Rho sine phi is how far that point on the floor is from the origin. And so that's what I'm going to need to turn the d theta into an arc length. So what we're looking for is this one down here. This is the questions. And this one up here is the one I labeled opposite angle phi. So the arc length, to turn this d theta into an arc length, I multiply by rho sine phi. Now all three of my factors in dv are lengths. d rho is a length because rho is just a length. Rho sine phi turns d theta into an arc length, and rho turns d phi into an arc length. So if we simplify that in spherical coordinates, dv is rho squared times the sine of phi, d rho, d theta, d phi. So this is the factor that we're going to use for dv when calculating triple integrals in spherical coordinates. The question comes up, why do we have to have r times d theta? Why is there an r in the dA for polar coordinates? Where does the r come from in the dv for cylindrical coordinates? Where does the rho sine theta or rho squared sine theta come from in spherical coordinates? Those factors are there to turn changes in angle into changes in length. So it's extra stuff that we have to put on the function that we're integrating so that our dv represents a volume. So in rectangular coordinates, we just need the function f of x, y, z. We need a dx, a dy, and a dz. I know I'm mixing my triple integrals with the spread out dv and then just integrate over w. I didn't want to write 3. If our function is in cylindrical coordinates, then I also need this r d theta, dr, dz. I need that extra factor of r to make the dv into a volume. And if we're in spherical coordinates, I need this rho squared sine phi to turn d theta and d phi into lengths. Those extra factors are there to make changes in angle into length. questions? The next thing we're going to want to do is describe some common shapes in the using all three different kinds of coordinates. But unfortunately for our hearers, I was super late to class today. So thanks for sticking around and waiting. I don't know what what amount of time you'll generally wait. The required amount of time is essentially 0 seconds, right? You could like walk by, see that I'm not in the room yet, even if it's like 10 to 12. It's like, well, Bleach isn't here, and then you just go. Because you could always either just zoom in or just watch the recording later. But I appreciate you sticking around for, what was like 12 minutes. That was ridiculously late today. So that we can get this, these different kinds of coordinates, just get us start thinking about these kinds of coordinates. The trick is noticing where the angles are measured from. Theta is always measured from the positive x-axis, positive x-axis towards the positive y-axis. Phi will always be measured from the positive z-axis down towards the point. So down towards the xy plane. Any questions? All right, that's going to do it for today. I will see you all on Monday. We have a good weekend, and thanks for playing.